Hi, this lesson is about approximating the area under a curve by using rectangles. But before we start with examples of that, we need to review summation notation. So summation notation uses this symbol that you see here on the left that I've rewritten here. This is the Greek letter sigma, and it actually means that you're going to add up all of the terms defined by a particular formula. And that formula is whatever this term here is. So a sub I is considered to be the formula for the ith term. Now, what does that mean, the ith term? Well, that depends on where you're at in terms of your counter. Notice that here I have something at the bottom of sigma notation that says I is equal to 1. That means you start from the first term, and then this one up here says that you end with the last term, and all those terms get added together. So think of this I as like a counter. It's called the index, where your counter starts where whatever I is equal to. Here I put 1, but it doesn't have to start at 1. And it ends at whatever the value of n is. Okay, so if we were to expand it, something like this. If you had the sum as j goes from m to n, so I use j instead of I. So I, j, and k are typical index variables that are used. Then that means that when you expand it, your first term is a sub m. Then your next term is a sub n, m plus 1. So you keep adding 1 to the index until you get to the last one, which is a sub n. And then all of those terms get added together to give you the value of the summation. Okay, so here are some linearity properties that summation notation has. So the first one says that if you take the sum of two terms, a sub j and b sub j, or the difference, that's the same as taking the individual sums and adding or subtracting them. The next one says that if you have a constant c in front of the term, well, that's a common factor to all of the terms that are being added together. So you can actually put it in front of the summation and then expand the summation as j goes from m to n of a sub j. And the third one says that if you take the sum of a constant, and this time I called it k, then that's the same as just multiplying n times k. And that's because with summation notation, that would mean that you would be adding k n times. So, and repeated addition is multiplication. So for example, if my k is 2 and my index goes from 1 to 3, that means that I'm adding 2 3 times. But that's the same as multiplying 3 times 2. So it's just a more convenient way to get an answer to multiply 3 times 2 than to add up individual terms. All right, so let's look at a couple of examples. Here's example 1. I have the sum as j goes from 1 to 4 of j cubed plus j plus 7. So I'm actually going to be able to use 2 of the properties above. I'm going to use the first one and the third one. So the first one is applied here in the very first line where I set up my summation in the original problem into 3 separate summations. Then I expanded the first 2. So the first summation of j cubed from 1 to 4 is 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. And then my second summation from 1 to 4 of j, well, that's right here, 1 plus 3 plus 4. And now my last one, the sum is j goes from 1 to 4 of 7. Well, that's where I can use the third property. That just means I'm adding 7 4 times, which is the same as 4 times 7. Okay, so in the next line, we just have to add all these numbers and multiply the 4 and the 7. So the first summation is 100. The second one is 10. And then 4 times 7 is 28. When you add those all together, the original summation has a value of 138. Okay, now let's look at the right. example 2, we want to evaluate the sum as I goes from 1 to 3 of ji squared plus 1. So this time I'm actually going to use I'm just going to plug them in directly the way it is. You don't have to split them up. You don't have to use these. You can just substitute in the values of I and still get the right answer. So that's what I did in line 2. I substituted 1 in for I in the first one, and then 2 in for I, and then 3 in for I. And then remember that I gets squared, gets multiplied by 2, and then we add 1. So when you expand it, actually do the multiplication and addition, you have 3 plus 9 plus 19, and that gives you a total of 31 as your summation value. All right, let's move on to example 3. So suppose that you have a sum as I goes from 1 to 12 of a sub I, and you're told that that sum value is 24, and you're also told that the first term has a value of -2. And we want to find the summation as I goes from 2 to 12. That's what we're trying to figure out. All right, so we know that our original summation, if you were to expand it, would look like this, what you see here on the right. A sub 1 plus a sub 2 all the way up to a sub 12. Now, if I took that sum and I subtracted or took away a sub 1, like you see on this next line, I'm going to subtract a sub 1 from the top line. Well, then the a sub 1s cancel each other out, and I'm left with a sub 2 all the way up to a sub 12 right here. But if I were to compress that into summation notation, well, that's just what you see here. That's the sum as I goes from 2 to 12 of a sub I, which is actually what I'm looking for. So the sum as I goes from 2 to 12 of a sub I is equal to the sum as I goes from 1 to 12 of a sub I minus a sub 1. Now we know the values here on the right, so I'm just going to plug it in the next line. So I get 24 minus -2, and that gives me a value of 26. Okay, here's one more. We want to expand the sum as j goes from 3 to 7 of k over j plus 1 and then simplify it. All right, so notice that my counter or my index is with respect to j, but I've got this other variable here, k. Well, k isn't going to change as j changes, only the j will change. So that's what you'll see here on the first line of work. When I expand it, it's k over 3 plus 1 plus k over 4 plus 1 plus k over 5 plus 1 plus k over 6 plus 1. Okay, then you simplify each of the denominators, just add the 3 plus 1, 4 plus 1, etc., and you get k over 4, k over 5, all being added, k over 6, and k over 7. So we need a common denominator. The LCD for 4, 5, 6, and 7 is 420. So the first term has to get multiplied by 105. The second one has to get multiplied by 84. The third one by 70, and the last one by 60. So when you add up all the terms in the numerator, you get 319 over 420 times k, which is what you see right here. Which is what you see right here in your final answer. Okay, so let's use some of this information to find the area under a curve that we'll call f of x, defined on a closed interval from a to b. And we're going to use rectangles to help us do that. So this first picture here is just an illustration of what I'm saying. We have a function f of x, which is indicated by this curve that I'm going over in blue. And so that curve, the area underneath that curve would be the area between that curve and the x-axis. And that's pretty much everything that's shaded in. Okay, but we don't really have a formula for that. We have formulas for geometric shapes like squares and rectangles, triangles, and circles. We don't have a formula to find the area under a curve. Okay, but luckily calculus allows us to actually compute that. Okay, so we start with estimates, and an estimate means it's an approximation to your answer. And we're going to use rectangles to help us do that. So if you can imagine this area getting split up into a bunch of rectangles, which you see here in the picture, if I were to compute the area of those rectangles, well, that would give me an approximation. And in some cases, I would get too much area because I would be above the curve. Like in this first one right here, this gives me more area than what I need. But in other circumstances, you're a little short, like here, where it's an underestimate. Okay, but when all of those areas of those rectangles are added together, you get a decent approximation. And as the number of rectangles increases, your approximation gets better. So remember that we're going to be using this formula since we're going to be using rectangles. The area of a rectangle is length times width. So in terms of our problem, you need the function value, which are all these points here. That will give you the height or the length of the rectangle, but your width is going to be based off of the difference of two consecutive rectangles. So if I would call this one x sub I and this one x sub I plus 1, then the difference between the two would give me the width of the rectangle, which we normally will call just a delta x, difference between the two consecutive x values. Okay, so some notation and formulas that we're going to need to use. We're going to let n be the number of rectangles used to compute the area. As I mentioned, the more n's you use, the more rectangles you use, the better your approximation is. Delta x will be the width of each rectangle, and we're going to compute delta x like this. We're going to take our interval AB, and we're going to subtract the greater value of the interval B minus the smaller value A, and divide by the number of rectangles. I will be the ith rectangle, where I goes from 1 to n, 1 being the first rectangle, and n being the last rectangle. And f of x sub I will be the length or height of the ith rectangle, because remember, we need a width and a length or height. So therefore, your area will be approximately equal to the sum of f of x sub I times delta x, which basically means that you are multiplying your width, which will be consistent throughout. So I'm going to just pull that out, and then add up all of the heights of the rectangles from the first rectangle to the nth one, and that computation will give you your approximation. Okay, so let's see this actually working for us in an example. So we want to estimate the area under the curve of f of x equal to x squared on the closed interval from 0 to 1 by using 4 rectangles. Okay, so that means that n is equal to 4. And if n is equal to 4, I compute delta x like this. It's 1 minus 0, we get this from here, divided by the number of rectangles, which is 4. So your delta x has a value of 1/4 or a quarter, which is what you see here. And that is the width of each rectangle. So I've illustrated that here in this picture. So if every rectangle has a width of a quarter, that means I need to create a table of values that show me the values of x starting from 0 and ending in 1, where the next consecutive number is a quarter unit away. So that's why we have from 0 to a quarter to a half to 3/4, and you can keep adding a quarter till you get to the end, which is 1. Okay, but now we need to know our heights or our function values. Well, that's this. So you plug in all of your x's, and you get the values on the right side of the table: 0, 1/16, 1/4, 9/16, and 1. All right, so now we are going to approximate our area by using 3 different options. We start with left-hand endpoints. What that means is that each of the rectangles has a particular height associated with it. And the height can be determined by either the point on the left side of the rectangle or on the right side of the rectangle. So what I mean by that is this first one here is rectangle 1, this is rectangle 2, this is rectangle 3, and this is rectangle 4. Okay, if I start with the left-hand endpoints, and I'll do these in blue right here, and this is the notation. Left-hand endpoints, that's the L, with 4 rectangles, that's the subscript here below, L sub 4. Okay, so the height of the first rectangle is based off of the left-hand endpoint. The left-hand endpoint happens to be at the origin. So it's kind of a weird rectangle, but it's basically a flat line. There is no height. That's okay, because that just means I'm underestimating my area on that first rectangle. Now I go to the second one. In the second one, the left-hand endpoint of the second rectangle is here in blue. If I extend across, well, that means that that's my area for the second rectangle. Again, looks like an underestimate. Now I go to the third one, pick the left-hand endpoint, extend that across. And again, this will be an underestimate of the area because I'm missing all this space here above. And then I go to the fourth one, pick the left-hand endpoint, draw that across, shade that in, and that is again another underestimate because I'm missing all of the space above. Okay, so how do we compute that? Well, that's when this table becomes handy. I'm going to be looking at the first 4 heights, starting with 0, ending at 9/16. Because remember, I'm not using this point up here at all. So I have length times width all throughout that computation, which is what you see here. Remember, the width is 1/4. So I have the width times the height, which is 0. The width times the height, 1/16. And again, I'm getting that from here. The width, 1/4, times the height, which is 1/4, and the width of 1/4 times the height of 9/16. Well, my width is the same all throughout, so I'm going to factor that out. So I have 1/4 times 0 plus 1/16 plus 1/4 plus 9/16. Then I need a common denominator for the expression inside of the parentheses. So I get 1/4 times 1/16 plus 4/16 plus 9/16, which is 1/4 times 4/16. When you simplify that, you get that your estimated area using left-hand endpoints is 7/32, which as a decimal is 0.21875. All right, so now we're going to repeat the process, but this time we're going to use right-hand endpoints. Just to illustrate that, I'm going to switch to the color green to be consistent with the color I used here. And so now if I look at rectangles 1, 2, 3, and 4 in my picture, and the height is determined by the right-hand endpoint, well, the right-hand endpoint of rectangle 1 is right here. And then we extend that across. So in this case, my height is here. So that's definitely an overestimate of the area under the curve. I've gone above the curve. Go to rectangle 2, same thing. Go across, and there we go. So that's my height for the second rectangle. Go to the right-hand endpoint of the third rectangle, and I have what you see here. Sorry, that wasn't so neat. And it's what you see here. And so my right-hand endpoint is again an overestimate. And then finally, I'll end at the last point on the curve, go across, and again, looks like I have more area than what I need, but still it's an approximation. So when you're looking at right-hand endpoints, you don't use the first one, you use the second one through the last. So that's what you see here. on the right. I have, try to keep that visible. So I have 1/4 times 1/16. 1/4 times a fourth. 1/4 times 9/16, and 1/4 times 1. Remember that 1/4 that's in front of each of them is the width, which we got from here, from computing delta x. All right, so since 1/4 is a common factor, I factored that out in the second line. So I have 1/4 times 1/16 plus 1/4 plus 9/16 plus 1. Then I got a common denominator of 16 in this line. When you add, you get 1/4 times 30 over 16. Simplify, that gives you that r sub 4 is equal to 15 over 32, which is 0.46875. So that means that my actual area is somewhere between this value here, 0.21875, and the one we just computed, 0.46875. Okay. A better estimate to use is what we call the midpoint of each rectangle. So in order to compute the midpoint of each rectangle, you have to go back to the original picture. And again, I'm going to switch just to a different color to be easier to read. I'll use purple. So in between each rectangle, there is a midpoint, a number right in between the one on the left and the right, the endpoints of the rectangle, and each of those has a height associated with it. So how do you find the midpoint? Well, it's basically the average of the first two values. So here, if I did 0 plus a fourth and divide it by 2, that would give me 1/8. And so that's right here. And then remember, the distance between each rectangle is still a quarter. So this one will be 3/8, this one will be 5/8, and this one will be 7/8. So, and each of those have a midpoint associated with it, a height associated with it, and those heights are here, indicated in purple. Okay, so that means I need another table in order to compute the function values at the midpoint. So that's here below. Remember, these were our original numbers. These are the midpoints that I just wrote on the graph. The heights, or the y values, are here. So that's the midpoint squared. So that's 1 over 64, 9 over 64, 25 over 64, and 49 over 64. All right, so that means that when I compute m sub 4, so the approximation using midpoints, it's your width, 1/4, times the height of each of these. Notice there's only 4, so you're not skipping the first one or the last one. You should be adding up the product of length and width for 4 rectangles, and that's what you see here. Then in the next line, I factored out a fourth, which is again the common factor. And then I need to add up all of my heights. When you add those up, you end up with 1/4 times 84 over 64, and that reduces down to 21 over 64. And if you write that as a decimal, that's 0.328125. Now, for now, you'll just have to take my word for it, but the exact area, not the approximate area, is 1/3, which is 0.33333 forever. So if you look at all of our computations, the left-hand approximation, the right-hand approximation, and the midpoint approximation, the midpoint approximation is definitely closer than the left and right-hand one. But they're all based off of computations of areas of rectangles. Okay. So as I mentioned earlier, as the number of rectangles n increases, the estimated area computed by L sub n, R sub n, or M sub n get closer to the exact area. But overall, M sub n provides a better estimate than L sub n and R sub n. All right, so let's do another example. We we want to estimate the area under the curve of f of x equal to 1 plus x squared as x goes from -1 to 2 by using 6 rectangles. So that means that your n is 6. And your delta x is, again, just the difference in your closed interval, which will be 2 minus -1 divided by 6, which reduces to a half. So every half unit, you need to compute a new height of the rectangle. So that's what you see here. We start with -1 and we end at 2, and in between you keep adding 1/2. So from -1 plus a half, that's where we get negative a half, then add a half, you get 0, add a half, you get a half, add a half, you get 1, add a half, you get 1.5 or 3/2. Your y values or your function values, you plug into f of x, which is 1 plus x squared, and we get the values on the right. Remember, to compute your left-hand endpoints, you start with the first height and end with the second to last one. So I have to multiply 1/2, the width, by all of the heights from 2 to 13/4. Then I get a common denominator, which is here. And that common denominator is 4. And when you simplify, you have an estimate of 5.375. We do the same thing for the right-hand endpoints using 6 rectangles. With right-hand endpoints, you start with the second one and end with the last. So these are L sub 6 and these are R sub 6. So same idea, you have the width, which is a half, then you add up all of the heights from 5/4 all the way up to 5, get a common denominator of 4 right here. Simplify, you have that the estimated area is 6.875. Now for M sub 6, you would have to do the same work we did above. You would have to get the midpoint of each of these. So for example, you would start with -3/4 and then keep adding a half till you get to the midpoint of the last two here. Add up all those heights, multiply by a half, and my M sub 6 is 5.9375. And so, as I mentioned before, for now you'll have to take my word for it. We haven't quite learned how to do this, but the actual area is 6. So my M sub 6 continues to be a better estimate than R sub 6 and L sub 6. Okay, but in comparison, if you were to do the same computations with only 3 rectangles, this would be the result that you would get. If you only use 3 rectangles, which is a small number, your left-hand estimate would be 5, your right-hand estimate would be 8, and your midpoint estimate would be 5.75. So even with only 3, your midpoint here with 3 rectangles is still better than your estimate with 6 using right and left-hand endpoints. And if we did 12 rectangles or 18 or 20, you would have an even better estimate, which would be even closer to this. Okay, so let's move on. So, as I mentioned, as n, or the number of rectangles, approaches infinity, these 3 values, your L sub n, your M sub n, and your R sub n, will all be the same value. Now, n approaching infinity means that's an awful lot of rectangles, because when you have infinitely many rectangles within the space, you won't be overcounting or undercounting your area. So to illustrate that, in this first example, I have 6 rectangles. So I am missing all of this white space here in my computation. But when I double that to 12, you can see that I'm missing much less space. So with n equal to 12, I would have a better estimate than when n is equal to 6, but it's still not perfect. Now, when n approaches infinity, well, these rectangles are so tiny and so close together that you actually are not missing or overcounting anything. This was 12 and this was 6. So you end up with this. So this is an exact area under the curve. Okay. So we're going to learn some new notation using this concept in mind, that as the number of rectangles increases, you get better approximation, and as it approaches infinity, well, you'll get an exact calculation. So therefore, the area under the curve of y equals f of x on the interval from a to b is defined to be this right here, the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I star times delta x, where, so there's some new stuff here that I need to explain, where delta x is b minus a over n. Remember, n is approaching infinity in this case, so it won't be a finite number. But it's still computed the same way. B minus a over n is the width of the rectangle. F of x of I star, well, that's the height in the ith rectangle. And it really isn't going to matter if you're looking at left-hand endpoints, right-hand endpoints, or midpoints, because as n approaches infinity, the rectangles are so skinny and tightly held together that you're not going to, it's indistinguishable whether you're on the left, the right, or in the middle. So that's what that star indicates. And there's different notations depending on the textbook that you're using and the author that developed it. Okay, so that summation that I just talked about is called a Riemann sum. And the Riemann sum is the definition of the area under a curve on a closed interval. So we want to use that definition just to express the area under the curve. We're not going to actually compute it. We just want to be able to express it in terms of the Riemann sum. So we're going to do that for f of x equal to x squared on the interval from 0 to 1. Remember, we already did this problem by approximating it. Now we're going to set it up so that we can actually evaluate it in future lessons, but we're going to use the Riemann sum to do the setup. So our delta x is 1 minus 0 over n, so delta x is 1 over n. Our height. Now our height is going to depend on the function value at each of the rectangles, and remember, it has a width of 1 over n. Now to illustrate it, I'm showing it to you, but in reality, these would be very tiny, very tightly packed together, so they wouldn't be visible to you the way these are here. But the first rectangle has a width of 1 over n. The second one is 1 over n units over, so that's 2 over n, then 3 over n, 4 over n. You get the idea, all the way up to n over n, which is 1, which is where the interval ends. Okay, so at any particular spot on those intervals, you can compute the function value by plugging into the function. So the first rectangle at 1 over n has a function value of f of 1 over n. And we know that I have to square that because of the definition of the function. The next one will have a function of 2 over n squared. The next one is 3 over n. So at some point, you are at some interval that's I over n, and the function value here will be f of I over n, which is I over n squared. So that's what you see here. I have my limit as n approaches infinity of the sum as I goes from 1 to n of f of I over n, that's your height, times 1 over n, that's your width. Okay, but my function is x squared. So in the next line, I'm squaring the I over n. So I have I over n squared times 1 over n. So if you combine all the n's, well, you get 1 over n cubed. I'm putting that in front of the summation because the n doesn't change as your I changes. The only thing that n is going to get impacted by is when you take this limit, and that's done at the end. So I have 1 over n cubed times the sum as I goes from 1 to n of I squared. And that's how you set up your Riemann sum. Okay, let's do another one. Now, to use the definition to state the area under the curve of f of x equal to 9x over x squared plus 6 on the interval from 1 to 3. So first compute delta x. We get 2 over n. Then we have to figure out what our function value is. Now, unlike here in the above example, where I start at 0 and the first value is 1 over n, here I'm starting at 1. So if you were to figure out, I'll just do this with a number line, starting at 1 and I'm ending at 3, whatever your function graph is. Well, the next one is going to be 2 over n units over. So this will be 1 plus 2 over n. And the next one will be 2 over n units more. So this is 1 plus 4 over n. And the next one will be 1 plus 6 over n. So the way you express that is that the input is going to be 1 plus 2i over n times your width, which is right here. This is your delta x. Okay, so the I represents whether you are, this is when I is equal to 1, this is when I is equal to 2, 1 plus 6 over n would be when I is equal to 3. So by expressing it like this, you are expressing it in general for any ith term. Okay, then we plug in 1 plus 2i over n into our function, which is what you see here. And so my summation, my area is the limit as n approaches infinity of the sum as I goes from 1 to n of 9 times 1 plus 2i over n divided by 1 plus 2i over n squared plus 6. Okay, let's move on to the next one. We want to determine a region whose area is equal to the given limit. So now we're going in the other direction. I've given you a Riemann sum. We're trying to figure out what would that be computing? What area would this Riemann sum here be computing? All right, so the delta x part is equal to pi over 7n. And remember, we get that value by subtracting b minus a divided by n. All right, so how would that occur? Well, that would occur if you have pi over 7 for b and 0 for a, and then the n is always in the formula. And if you resolve that, you would get pi over 7n. So that's your interval would be from 0 to pi over 7. And your function, well, your function is clearly tangent. And my input values is I pi over 7n, because for every ith interval, you have a new space, a new part of the a new rectangle for you to input into the function to get its height. So my function is tangent of x. So the limit represents the area under the curve of y equal tan of x on the interval from 0 to pi over 7. Okay, so now you're ready to try the homework for 5.1. Good luck.